a challenge.
Yeah, it was really bad. Okay, so yeah, constraint optimization. So what we looked at last time, and yeah, like what we've been looking at so far, was a case where we just have an objective function and then we're trying to maximize or minimize the objective function. But now, practically, they are like what we face as people is actually what we call constraint optimization, because you might find that you want to utilize, also you want to maximize your utility, let's say from the consumption of two goods, let's say Coca-Cola and Fanta, but you have a restricted, more like you have a fixed amount of income. But your goal, of course, is to maximize this consumption. You want to buy both of these commodities, but you don't have enough income. You are limited. There's a limitation. So, when faced with such a problem, we use what we call constraint optimization. Given that you only have, let's say, 100 kwacha, and from this 100 kwacha you want to consume both commodities, good X and good Y, how many units of good X and good Y must you buy for you to maximize your utility, given that you only have 100 kwacha? Yes.
Yes.
So basically this is what we really face in real life situations. So we call this constraint optimization.
Yeah.
Yes. So really, the goal is the same. We want to maximize a given function, but now we want to do this given that we have a constraint. Yeah. Yes. So we usually use what we call there's what we call the Marshallian demand functions. Yes. So for us to derive the so-called Marshallian demand functions, we are supposed to use what we call the Lagrangian equations. So we are going to go step by step because this is a somewhat
These, Jesus Christ, these cartoons.
No, we'll try
Here
to.
you do somersault. I've seen the way they take. At the somersault, Tom and Jerry chasing each other. Yeah.
No, we'll try to understand these things like step by step. I'll be as slow as possible because my target is not finishing the content today, but you understanding the concept.
To understand the concept and how you just derive these things.
Yes.
Because I've seen, there's a very serious link between quantitative analysis and micro.
Yes.
A very serious thing, such that if you're able to, because even in microeconomics, there are these things, you find them. So I think if you understand them, you'll be able to. At Shan, if you doesn't learn that with one stone, Shan.
You'll be able to kill two birds with one stone.
At killing one bird is, two birds with one stone. Okay.
Yeah, okay, so let's try this.
Yes.
Alright, so really what we want to do practically is confirm if you're able to see the PowerPoint.
Yes, I can see it.
Okay, so yeah, in real life situations, we have issues where we have, let's say we want to maximize the utility from consuming two goods, good X and good Y, but we are faced with a constraint of finances, income. So mathematically, we know that if we have a level of income, let's say 100 kwacha, and the price of good X, let's say, is let's say is 2 kwacha, and then the price of good Y is, let's say, 5 kwacha. What we want is, given that these are the prices of these two commodities, and since we want to consume these two commodities, we must know the maximum amount of good X. Given that the price of good X is 2, we should also know the maximum amount of good Y, given that the price of good Y is 5. We need to know the maximum of these two commodities that we can buy, given that our income is 100 kwacha. So this is where
and my desire is to maximize my utility by spending my budget 100 kwacha.
Yes, given
that's
that
economies.
Exactly, given that we have these two prices for these two goods. Yes, so that is the goal. So there's what we call a budget constraint, or sometimes they'll ask you to come up with a constraint, a budget constraint. So what we do is this: we know that I have to buy X units of good X, and at the same time I need to buy Y units of good Y, given that my income is 100 kwacha. Yes, but at the same time I know that these units of good X, these units of good X, I will not just get them for free, because there's a price attached to good X. So this means that when I get the price of good X, I multiply that by the units of good X. I do the same with good Y. I get the price of good Y, I then multiply it with the units of good Y. This should give me this should equal the amount of income that I have. In short, we cannot consume beyond our income. Yes. So since we cannot consume beyond our income, it makes sense to say that the sum of these two on my left should equal the level of income, the 100 kwacha. What this shows is that we cannot consume beyond our income. So in microeconomics, there is what we call utility maximization using the indifference curves. I don't know if you've seen that before, but
yes.
So what we are saying is that, given that your budget constraint or your budget line is this line here, and then this is your indifference curve, you cannot consume beyond this budget line. Therefore, we just need to find the units of good Y and X that will maximize our utility, given that we only have this 100 kwacha. Yes. So this is the goal of constraint optimization. So now we are saying that for us to do this work, we need to use, or we need to derive the Marshallian demand equations. But again, for us to derive the Marshallian demand equations, we need to use what we call Lagrangian equations. Yes, we need to use the Lagrangian equations. Lagrangian equations. So, and now these Lagrangian equations, they use what you call it's more like a chain. This uses this uses that. So the way we set up, or let me first help. Let's go through the steps together. So we know that we need to derive the Marshallian demand functions or equations, and for us to do that, we need to use the Lagrangian equations. So the first step in deriving the Marshallian demand functions is to set up the maximization in terms of the Lagrangian equation. Yeah? Okay? Yes. So now, this thing called the Lagrangian equation comes in this form here. Okay? So let me use PowerPoint now. So that we yes. So these things called the Lagrangian equations, the way we set it up, because we know already that we want to maximize utility, which is a function of two goods, good X and good Y.
X and Y.
Yes. At the same time, we know that the price of good X multiplied by the units of good X plus the price of Y multiplied by the units of Y should equal to the level of income, which we are calling I. Yes.
Yes.
Yeah. So what we want is to maximize this. But how do we maximize this? We need to set up a Lagrangian equation. Now, the format of a Lagrangian equation is like this. We are going to come up with a function which we are calling L. And this function L should be a function of good X, or the units of good X, the units of good Y, and another third thing which we are calling the multiplier or lambda. This kind of thing here. This kind of thing. Okay? So, now we are saying that we should come up with a function L, and this function should have X, should have Y, should have lambda. Okay? So now, how do we do this? So we know that we want to maximize our utility from consuming two goods, good X and good Y. Okay? So in short, what it is you get the objective function, that function in the first, which initially has got X and Y, it should be the first thing to write. Okay? So after writing it, so the utility function, which is a function of good X and Y, and then you say that function plus, now you come and put lambda, you open the brackets, you put the, what we call the inverted constraint, where now you get the Y, or you more like you get everything that is on the left side of the constraint, you take them to the right.
Right. Okay.
So this is going to become, so I, you are going to say I, then when Px, when the price of good X multiplied by X crosses the equal sign, it's going to become minus. Okay? So it's going to become minus Px multiplied by the units of good X. Then again, this Py times Y, when it crosses the equal sign, it's also going to become minus. You have Py multiplied by the units of Y. Then you close the brackets like that. So in short, what we have done this far is setting up the Lagrangian function, or the Lagrangian equation. Okay? Now, there is more to this, because what we have done is just the setting up the Lagrangian equation. Okay, so let me quickly look for a like an actual equation, or let's just make assumptions.
Okay.
Yeah, let's just make assumptions that we have a function. Let's say utility is equal to, let's say, I'll use an example that I gave. I was giving a quiz to these guys last week. So let me look for the function. Okay, I have it. So we had u xy x1 x2, yeah. Then this was equal. The function was like this: x1 x2 subject to So we had 4x1 plus 2x2 is equal to 60. So this is good because now we can do the practical part even as we are deriving the Marshall. So if we've been given a function like this one here, utility is equal to x1 x2, which is equal to this one. Okay, so in short, this is what we call our objective function.
That's x1 x2.
Yes, x1 multiplied by x2. So we want to know the maximum units of good x1 and x2 that we can buy, given that this is our budget constraint.
Okay.
Yes. So from this budget constraint, we know that this 4 is the price of good x1. All right. And then this 2 is the price of good x2, and the total level of income is 60. Okay? Is that okay? Hello, is that okay? Can you hear me? Can you hear me, ma'am?
Yes, it's clear.
Oh, okay.
Yes, George, it's clear. Yes, I can hear you. You are able to hear me?
Yes, I can hear you.
Yes, I can hear you. Are you able to hear me?
Yes,
Okay.
I can hear you, yeah. Can we continue? I'm scared about that problem for last time.
Oh, okay.
Okay, let's try to carry on.
Okay.
Okay, so yeah, we have this function x1, x2, and then we have our constraint here, for x1 plus 2x2 is equal to 60. So we want to maximize this. So we've said that this is our Lagrangian. We've managed to set up a Lagrangian function or Lagrangian equation. So now, practically, how do we do this? Okay, practically, how do we solve this function here? So the first thing to do is to get the partials. All right, is to get the
Yes.
Yeah, the first thing is to get the partial derivatives, which means that we're supposed to get the partial derivative with respect to x. We should also get the partial derivative with respect to y. At the same time, we will also be forced to get the partial derivative with respect to, so this thing called the the comma symbol here represents this one here. We call it lambda. Yes, we call it lambda. So we will be forced to get the partial derivative with respect to x. We'll also be forced to get the partial with respect to y, and then lastly we'll also need to get the partial with respect to lambda. Then we are now going to see what follows. So let's try to use the notes. So what we've done is setting up this function.
Okay.
What we've done is trying to set up this function here. Okay, that the function L is going to contain three things: x, y, and lambda. which is equal to, so we are going to put our objective function, then plus lambda open brackets, we take px x py y on the other side, meaning that after crossing the equal sign, both of them have to be negative. Then now we are going to try to get the maximum values of x, y, and lambda. Yes. So of course, the first thing is to set up the maximization in terms of the Lagrangian equation. Yeah. Then after that, we need to get the first order conditions, which are just the partial derivatives of these three variables. Okay. Yes. So now, remember that we have this function here, the one we are trying to maximize, this function. So now, if we were to get a partial derivative, so that's this comma sign here, it means partial derivative. So if we want to get the partial derivatives of partial derivative of L with respect to x, what it means is that we are just going to differentiate this function throughout with respect to good x. Okay. Then let's do this together so that we derive them together. Yeah, so we know that we have a function L which has got x, y, and lambda. Yes, which we said is equal to u x1 comma x2. Yeah, then plus we include our lambda. Then now we have got I minus
x
plus
minus.
Oh yeah, it's supposed to be minus. You're right. It's minus. Yeah. It's
okay. Now focus to remove.
Yeah, minus py y. Yes. So now what we want is now to get the partials. So change in L due to change in x. Now the way I usually, especially when I'm teaching about this, I don't rush to getting the partials, but opening up the brackets here, these brackets.
Okay.
Yes. So we know that this will give us L is equal to, okay, so L is equal to, so we've got u x y, and then you say plus. Let's try to distribute the lambda throughout.
Okay.
So lambda times I, we're going to have lambda I. Then lambda times negative pxx, this will give us minus price of good x multiplied by the units of x. Lambda. And then I'll do the same minus lambda times this, give us lambda price of y multiplied by the units of y. Yes. Now we can do the partials now. So change in L due to change in x.
And px price of good x by x. We've left out lambda. Is it okay?
Wow, you are following. This is good. Okay, so let's put our lambda there. We put the minus there. Yes, that's okay now, right?
Yes.
Okay, perfect. Yeah, so now we can now get the partials. So it like when you open the brackets, it's more like work becomes a bit simplified,
easier.
Yes. Yeah, so now we want to get the partials. Okay, so now when you look at from this part here, there's x here, and then there's also x here. All right. So x, we have got x in the utility function. We also have x in
X in the constraint.
Exactly, yes. So now, what it means is that from the constraint, we are going to partially differentiate this constraint with respect to x, right? So this is the same thing as saying we are going to partially differentiate the objective function here, okay, with respect to x, right? So this whole function here is positive. No wonder even the derivative is positive. Okay, but when you go to the constraint side, this part is negative, right? I've got negative lambda pxx, which means that even here we should put a negative. Okay, so what it shows is that now look at this px, right here, pxx and lambda. We want to differentiate this part here, right? But when you look at it critically, you're going to notice that the x, okay, this x, so when you differentiate the x is raised to the power 1. Remember, it's partial, right? And this x is raised to power 1. When we differentiate this x to power 1, it's more like there's a 1, of course, on top. We do the minus, you know those things, right? So at the end of it all, we are going to remain with the lambda px. Do you agree? Do you agree? Hello? Hello, can you hear me?
Yes.
Okay. So, we want to differentiate this part, the lambda price of good x times the units of good x. Now,
yes, I agree.
Oh, okay. Wow, it's taking long.
Hello.
Hello.
Network.
Can you hear me? Hello, can you hear me? Maybe to deal with the network, try to disconnect your video, you see? Your camera, you see?
Yes, to load. Hello. Yes, I can hear you. I do what? Oh.
Yeah, try to disconnect.
Okay. Then I connect.
Hi? Okay, how is it now? And you can see the screen, right?
Your screen. Project, I see.
Okay, let me try. How is it now? Can you see it?
Yes, I can see it.
Okay, alright. Okay, we are facing the same challenge where when I speak, it's taking ages for you to to here.
To get feedback.
Yeah. Okay, yeah. So, okay, so we have managed to set up the function, right? And now we are trying to get the partials to them, and we really need to try to move.
Oh, yes.
Yeah. Okay, yeah. So we have managed to set up the function, and we've opened the brackets here, and now we are saying that let's try to get the partial derivatives with respect to x first, and then we're going to do the same for y and do the same for lambda. Okay, yeah. So we have said that for this part here, from this utility function, we are just going to partially differentiate the utility function with respect to x. And since it's positive here, even its derivative should be positive. But when you go to the constraint, we have negative lambda price of x multiplied by x, which is this one here. Now, when we differentiate this, this is just going to be more like we are differentiating it with respect to x1 because this is partial.
Yes.
Okay. So now we know that this x, but remember we're differentiating lambda price of x times the units of x. So we want to differentiate this with respect to the units of x. But this thing x here is raised to a number 1. And we know that every time we differentiate something that is raised to power 1, it just collapses. It collapses to 1. So it's more like after differentiating this whole thing, we are going to have lambda price of x.
Yes.
Right? And we know that using the first order condition, this is supposed to be equal to 0.
0, yes.
So we have just done for x. How about y? So we do the same. Change in L due to change in x. Oh, sorry, in y now. In y. It's going to, so we're going to do the same. From the utility function, we are going to partially differentiate the utility function with respect to y. Minus, okay, minus, we do the same for this part here containing y, right? So you know that the same thing, y is raised to the power 1. When this thing is differentiated with respect to y, we're just going to have lambda price of y. We equate this to 0.
To 0, yes.
And then lastly, we should also get the change in L due to change in lambda. Okay.
Lambda.
Yeah, so change in L due to a change in lambda. We should equal, we know now that lambda is only present from this side up to there in the constraint, right? We have got lambda there, we've got lambda here, we also have lambda there. Yeah, so we know that since we have lambda I, when the moment to differentiate this with respect to lambda, we're just going to remain with I. Okay.
Only,
yes. So we have got I there minus here. When you differentiate this, which is this, we have got negative lambda price of x times x. When you differentiate this whole thing with respect to lambda, we're just going to remain with the price of x multiplied by the units of x, right? In short, yeah. Anyway, yeah, I'll show you when we do the actual equation. Okay. Again, here we know that if we differentiate this with respect to lambda, we're just going to remain with the price of y times y. So we have price of y times the units of good y. So now what this means is that we now have the first order conditions.
Yes. Are we equating this one to 0 as well?
No, this one, yes. Since the first order condition, yes. We equate it to 0. Yeah, since it's the first order condition, equate it to 0. Okay, so what we've done so far is setting up the Lagrangian function, then getting the partial derivatives with respect to x, y, and lambda. So now the next step is to more like simplify these, to simplify the equations. Okay. Okay, so let's try to go back to the notes and see what's there. Just as I've said, the next step is to simplify the equations. Okay. So in short, the moment you get the first order conditions from each function, you can see that here we have lambda, there we had lambda, and in short, from equation 1 you make lambda the subject of the formula. From equation 2 you also make lambda the subject of the formula. That is what that is what C and D basically are talking about. So C is saying simplify equation 1 to get the value of lambda here. Okay, so in short, can we try to make lambda the subject of the formula? Okay, so let's go back to our PowerPoint. So let me come up with another. So previously on that page we had change in L due to change in a good x. We said that the answer was supposed to be, we partially differentiate the utility function with respect to x. Yeah, then minus, we had lambda price of good x. Yeah, we had the lambda price of good x, right? Then we equated this to 0. We also had anyway, let's start with this one first before looking at the other one.
We go on step by step.
Yes, step by step. Yes, step by step. So now what C is saying is saying that can we simplify this equation? In short, from this equation, can we make lambda the subject of the formula?
Okay.
So since we know that change in the utility function due to respect with x minus lambda price of good x is equal to 0, right? What we can do is taking lambda the other side, so that we make lambda the subject of the formula. Okay?
Yes.
So in short, we know that change in u due to change in x is equal to lambda price of x. So look at this. Before lambda px crossed the sign, it was negative.
Yes.
But after transposing to this side, it has now become positive. So we now have so in short, we've just taken lambda px on the other side.
Okay, together with the px.
Yes, together with the px, because these are multiplicative, so they move together. Whatever. Yes, exactly. So remember that our key is to make, or our aim is to make lambda the subject of the formula. So the only way we can do this is by, here we divide by px, and remember, whenever you have got an equal sign, whatever you do on the right should be done on the left. Whatever you do on the left should be done on the right. Yes. So since here we've divided by px, which means that even on the left we should also divide by px.
Yes.
So that the px on top here and the px down can cancel. Meaning that our function is now lambda is equal to change in u due to change in x, everything divided by price of x.
Yeah.
That's okay, right? Okay. Now we can do the same with y. We can do the same with y. What it means that even that one, which is the partial with respect to y, we can also make lambda the subject there. Okay, so how do we do that? We just do the same steps. Remember, we had the function which was the change in L due to change in y. We said it was equal to the derivative of the utility function with respect to y minus lambda price of
PYY.
Exactly. We had py. We had px. We had py, right?
Yes.
Then this was equal to 0. So we can do the same thing while saying that, okay, to make lambda the subject, should take this term lambda py on the other side. So change in u per change in y must equal lambda times py, right? And now to make lambda the subject, we are just going to divide here by py. We also do the same here by py. Yes, so that here we can cancel. We remain with lambda is equal to, right? We're together? Yes.
Yes, I'm following.
Okay. Yeah, so we cancel this. We're going to remain with lambda. So lambda is equal to change in u due to a change in y, then everything over price of y. Yes. So now from here, okay, or so far what we've done is setting up the Lagrangian function, getting the partial derivatives with respect to x and y, and then we have made y the subject of the formula from both equations. Yeah. So the next step now, because what we've done is we've said, okay, lambda from the x equation, lambda is this, and then from the y equation, lambda is this. Okay?
Yes.
But lambda is lambda, meaning that we can equate these two equations, because here we are saying that lambda should equal this one, and then here we are saying that lambda should equal this one, meaning that change in u per change in x divided by the price of good x must be equal to change in u over change in y divided by the price of y. Right? That's okay, right?
Price of the y.
Okay, so how is it going so far? Hello, how is it going?
So far, so good.
Yeah, okay.
So far, so good.
Okay. Alright, so now, since lambda is equal to this, lambda is also equal to that, the next step is to equate these two guys. Okay? In short, we are saying that lambda is equal to lambda. And we know that lambda from this side is change in u, change in x over px. Yes. So this whole term should equal this other side here. Okay? So it should equal change in u, change in y over py. Okay. Now we have to simplify. Okay? yeah, now we have to do the simplification so that we can finish the magic. Yes. So now, when you reach at this stage, okay, when you reach at this stage, basically, what we are saying is that the ratio, so in microeconomics, there is also what we call the marginal rate of transformation. Okay, marginal rate of technical. Yeah, this is supposed to be marginal rate of marginal rate of substitution. Yeah, since it's under utility.
Oh yeah.
Yeah, marginal rate of substitution, and the marginal rate of substitution is just equal to partial of u due to change in x, okay, over partial of u with respect to y, and this should equal price of good x divided by price of good y. Okay, all right. Are you there?
Yes, I'm here.
Okay. Yes. So now, in short, at this stage that we've reached, we have reached at the equimarginal principle, which states that given two goods, good x and y, the marginal rate of substitution of good x divided by the marginal rate of substitution with respect to good y must equal the ratio of the prices of these two goods, x and y. Okay? So in short, when you reach at this stage, where you have partial of u over partial of x divided by the price of x is equal to partial of u over partial of y divided by the price of y. You have reached at the stage where we call this the equimarginal principle. Okay, equimarginal principle, and this principle states that at equilibrium point, in this case at utility maximizing point, okay, the marginal rate of substitution of good x divided by the marginal rate of substitution of good y should be equal to the price of good y over the price of should be equal to the price of good x over the price of good y.
Good y.
Yes. Okay. And now we know that the marginal rate of substitution with respect to good x, okay, the marginal rate of substitution with respect to good x is just the rate at which utility will change due to a change in x. Okay? In short, if I consume an extra unit of good x, how is this going to affect the satisfaction that I'm getting from consuming this particular good? Okay, so in micro, in economics, this is represented by the equimarginal principle, which states that the marginal rate of substitution of good x divided by the marginal rate of substitution of good y must equal to price of good x over price of good y.
Price of good y. Okay.
Exactly. So, in short, the final thing to do is getting the equimarginal principle, which is the change in utility due to change in good x over the change in utility due to change in good y. These two sides must equal to price of good x over price of good y.
Price of good y.
Yes. So when you reach at this stage, then it means that you are done. You have managed to set up the Lagrangian function. You have also managed to get the partials with respect to good x, good y, and lambda. And lastly, you have you know you found lambda from x. You also found lambda from y. You equated the two. Yeah, you equated the two so that you can reach the equimarginal principle.
Okay.
So this is what is supposed to be done.
Nishi hapo
hapa. Okay. So can we now try to hammer this kama question that I gave these guys? Can we try that together, of course?
Where you substitute the numbers?
Yes. Okay. So I gave these guys the full timers. Gave these guys this simple quiz. They failed. Gave them a makeup. They are also failing because I was
a simple quiz, George. Jesus.
The simple one.
Yeah, I wish it's interesting if you do it like a 4-year program. Like you just come as an undergrad, you start the basics, then you start rising with everything.
Anyway, it's okay.
They will understand, I'm sure.
Yeah, they should understand.
You do your very best.
Because I try my level best with these guys. Yeah. Okay, so I gave them this simple question. I wanted them to maximize it. Yeah. So let's try to solve it. We show them what they were supposed to do. All right. So we have two goods, x1 and x2, and then this is the utility function. So utility is equal to x1, x2, and then this was the constraint. This was the constraint. Okay. So can we find the utility maximizing quantities? Okay. Can we find the utility maximizing quantities? So we know that the first thing is to set up the Lagrangian function. Okay. So L is equal to x1, x2 plus lambda. We open the brackets. Okay. We write our 60. Then these guys should cross the equal sign. So this will become minus 4x1 minus 2x2. Yeah.
Oh, now this is
you're now getting the logic, right?
6.
Say that again. You are breaking.
x1 minus 2x2. Close bracket.
Hi, you are breaking.
I
try to.
It's good.
Yeah, I can get you now. Hello?
Okay.
Hi, can you hear me?
I can hear you clearly.
Okay, now the network has stabilized.
But you're not getting me.
I can now get you.
Okay.
Okay. Yeah, can we continue?
Yes, please.
Okay, perfect. Yeah. Okay, so now we have our Lagrange. We now have our Lagrange. Yeah. Next thing is to get the partials, right? You need to get the partials. So change in L due to change in x1, okay, is equal to, so we know that x1 and x2 they are multiplied. So but when we differentiate this with respect to good x1, we're just going to have good x2, right?
Yes.
Good. So we're going to have x2 here. Or in short, let's do just the same thing we've done there. Let's first open the brackets to make things
Let's
simple.
open, yeah. I actually wanted to say that.
Okay. So I've got
Yeah.
x1, x2 here, plus, so I'm going to have 60 lambda. 60 lambda minus 4 lambda x1, then minus 2 lambda x2, right? Yeah, now let's get the partial. Yeah, so change in L.
Okay, yes.
Yeah, change in L due to change in x1 is equal to, if we differentiate this with respect to x1, we are going to have x2, right?
Yes.
Yeah, so I've got x2 here, and then minus x1 is also appearing here. So if we differentiate this with respect to x1, what are we going to have?
4 lambda.
4 lambda, yes. We equate this to 0.
I didn't write my lambda properly. I'm looking at it like a y.
Oh.
4 lambda.
I see. Then again, change in L due to change in Y. Change in Y. To x2, sorry, not Y.
This is x1.
Yeah.
X2.
So change in L due to change in good x2. This will give us, yeah. So from here, we're going to have x1. Then from here, if we differentiate this with respect to good x2, we're going to have minus 2 lambda.
2 lambda, yes.
Yeah, we equate this to 0. Yeah. Then lastly, we should also get the change in U, also change in L due to
change in L over due to change in lambda.
Yes. So you know that from here, if we differentiate this with respect to lambda, we're going to have about 60
minus 4x1
minus
2x2.
We equate this to 0 as well, right?
Okay, equate to 0.
Okay. Right? So now,
yes.
The next step is to, we know that from this equation, we should make lambda the subject. We'll do the same in this other equation here. Make lambda the subject. Then we equate the two.
Yes.
Good. Alright, so let me just open another page, Excel page. Yeah, okay. So we had change in L due to change in x1 was
x2.
Yeah, we had x2
minus 4 lambda equals to 0.
Yeah, 4 lambda is equal to 0. And then we also had change in L due to
change in x2,
which gave us
x1
minus
2 lambda equals to 0.
Yes. So now, from this first equation, we should make lambda the subject. We do the same in the second equation.
Yes.
So, let's start with the first equation. We have x2 minus 4 lambda is equal to 0. Okay? So, we know that we can just get the negative 4 lambda the other side.
True.
So that we can have x2 is equal to positive 4 lambda, right?
4 lambda, yes.
They will divide both sides by 4. So that we cancel the 4 and the 4, mean that our first lambda is x2 over 4. Yeah?
Okay.
Yeah. We do the same in the next, this other one. Okay. So we can say x1 minus 2 lambda is equal to 0. Yeah. So that x1
equals
positive
2 lambda.
Yes. We divide both sides by 2.
Then lambda is equal to x1 over 2.
Exactly. Yes. Yeah, I love that. So now we have lambda 1, we also have the other lambda. Meaning that we can equate these two
to each other.
Yes, to each other. And then we solve for x1 and x2.
x1, 2.
Yeah. Right? So we say lambda is equal to lambda, right? So we say x1 over 2 is equal to x2 over 4. Right? Yeah. Okay, let me just erase this. Therefore, what we can do is making one of these the subject of the formula, either x1 or x2.
Or x2, okay.
So, if we cross multiply here, you know about cross multiplication, right? Okay. So if you cross multiply here, we're going to say x1 times 4, which will give us 4x1.
4x1
is equal to 2 times x2, we have 2x2, right? So let's say we divide both sides by 2 so that we make x2 the subject. So those 2 and that 2 will go, meaning that wherever there is x2, we should put, so 2 into 4, we know it's 2, right?
It's 2, yes.
Yeah. So wherever there is x2, we are going to put 2x1, isn't it? So that we go back to our constraint.
Yes.
We go back to our constraint. And our constraint is saying that 4x1 plus 2x2, the total level of income should be 60.
60, yes.
And we are saying that wherever there's x2, should put 2x1. Right? So we are going to say 4x1 plus 2, but wherever there's x2, should put 2x1.
2x1, yes.
Is equal to 60.
2, then we have 2x2 brackets is equal to 60.
Yes. So now we can open the brackets, right?
Yes.
So for x1, then this will give us plus 4x2, for x1 again, is equal to 60, right?
4x1 plus 4x1, correct?
Yes.
Is equal to 60.
Yes. Okay. Now we can add 4x1 plus 4x1, giving us
8x1. Okay.
is equal to 60, right?
X1, yes, it's equal to 60.
But our aim is to find the value of x1, right?
Yes.
Yes.
So
So
we
how do we do
divide.
that? We're just going to divide both sides by 8, isn't it?
By 8, yes.
Which means that x1 is equal to, so 60 divided by 8, this is 7.5.
7.5, yes.
So what we've done is finding, or in short, we now know that for this consumer to maximize his utility, at least he should buy 7.5 units of good x1. Okay? How about x2? We have a function which is saying that x2 is equal to 2x1, right? So therefore, x2 is equal to 2 times, but we now know what x1 is.
Yes.
That is 7.5.
7.5.
Yes, therefore, 2 times 7.5, we have 15 units of good x1, of good x2.
Okay, x1. Just go back there. How to find the units for good x2.
Okay, fine.
Are we going back to the constraint? Also?
So, remember that after equating lambda is equal to lambda, we had x1 times 4, we had 4x1 here over.
Yes.
We had 4x1 is equal to, then 2 times x2 we found, so in short we had 4x1 is equal to x2, right?
Yes.
We had to equate, we had to divide, both sides by 2.
Yes.
So that we make x2 the subject of the formula. Remember?
True. Yes.
After this, we went to the constraint, replaced x2 with 2x1. We solved and found that 4x1 plus 4x1 is equal to 60.
Yes.
Then 4x1 plus 4x1, we had 8x1 is equal to 60 here.
And we divided.
We've divided.
To find 7.5.
We found x1 to be 7.5, right? So now to find the units of good x2, remember we found an equation that is describing the units of good x2 that can be purchased, and we said that x2 is equal to 2 times x1, right?
Yes, x1.
So
yes.
So we had this equation here, x2 is equal to 2 times x1, but now since we know the value of x1, that x1 is 7.5, okay, therefore x is
understand.
Perfect. So you just replace it. You replace and solve. So this is the application of
by the value for x1, which is 7.5.
Yes.
Okay.
So this is the application of constraint optimization.
15 x2. Okay.
Okay, so this is how we apply.
It's interesting.
Oh, okay.
Yeah, it's interesting.
Oh, that's good to hear. Most people run away from this topic.
You can run away, George. I can't blame them. Hey, you can run away.
Wow.
But you tell yourself to say, I just have to know this.
Yeah. And indeed, we just have to know this. Okay, yeah. So what we've done in the first place, we have just like using the symbols and all those things, trying to.
These are symbols.
Yeah. Okay. So in short, they can either give you the actual functions, like the one we're just from doing now, and they ask you to get x1 and x2, or there are times when they just want you to use these symbols. So you know that, well, given a utility function that has got two goods, x and y, I should first come up with the Lagrangian function. Okay, should first come up with a Lagrangian function, and then after coming up with a Lagrangian function, I should maximize it. Okay, and how do you maximize it? You know that, well, it's just to find these first order conditions. You find the first order conditions, you go to x and y, you make lambda the subject. Okay, lambda from the x equation, you also get lambda from the y equation. You put these two together using what we call the equimarginal principle, which is the partial in the utility function with respect to x divided by the partial of the utility function with respect to y. This ratio must equal the ratio of the prices.
Price of x and y.
Yes. Then from here, you know that you are done.
Practice makes perfect.
Practice makes perfect. You are right. Yes, perfectly right. Okay, so
do you have a question which I can remain to try? You can enter.
Okay. Let me just find the question just about now.
Yes, find the question, then you WhatsApp.
Okay, Mama. I will do just that.
Okay, thank you very much. My head feels saturated.
Oh,